Namaskar. I am Rudra Kafle from Worcester, Massachusetts. Today, I am transmitting this brand new episode of Physics is Fun. This is 13th episode, right? So, if you missed the previous episodes, they are all available in Facebook, in my account, or in YouTube. Okay, in YouTube I have uploaded all those past episodes. You can watch in there. So today I will be a kind of extending the Newton's laws applications and going slightly beyond. So we know Newton's laws of motion already, right? There are three laws of motion: Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. And in the very beginning, I believe in the first video, I mentioned that if we understand Newton's laws of motion, we understand most of the universe. Okay, most of the universe, not everything, but we understand by understanding Newton's laws of motion, we understand a big chunk of universe. Okay, so today what I am going to do is how is force related to work, energy, work and energy basically. Let me talk about those two things. Okay, so I will do a small demonstration to you, and then I'll go to mathematics. Okay, mathematics it makes physics, understanding of physics better, right? So I have an apple in my hand. So this is an apple. In the very first episode, I told you that the mass of an apple, the average, about an average sized apple has mass. Do you remember how much was that? Right? I mentioned that in the very first episode. An average sized apple has mass of about 100 grams. Right? So mass of an average size apple is 100 grams, right? So, or you can convert that, divide by 1000, that is 0.1 kilograms, right? So you know the mass of apple, of average size apple, right? Not very small apple or not very large apple. An average sized apple has mass of 100 grams, which is 0.1 kilogram. Okay, we know that. And so on the surface of the earth, the acceleration due to gravity is about 9.80 meter per second squared, right? So that is acceleration due to gravity. If you multiply those two quantities, mass and acceleration due to gravity, so then what we get is the weight, right? So we know the weight of this apple, right? So 9.8 times 0.1, which is 0.98 Newton. And I told you at the time, approximately it is about 1 Newton, right? Approximately it is about 1 Newton, because 0.98 is very close. 0.98 is very close to 1, right? 0.98 is very close to 1. So its weight is about 0.98 Newtons. Okay, or approximately 1 Newton, right? So what I do is the object is the apple is on the top of the table, right? So I lift this apple to, let's say, about this height, which is about 50 centimeter. Okay, so this is 30, and about from here to there is, let's say, about 50 centimeter. So what I am doing is I am lifting this apple from the top of the table to a height of about half meters, which is 50 centimeters. So what we say in physics is we do work. So I am doing work. I am doing work in lifting the apple against the gravity, because gravity is pulling down. Gravity is pulling the apple down. So I am applying force, let's say about the same amount of force, right? And I just overcome that, right? I just overcome the gravity and lift about half meters. right, above the original point, right? So when I do the work, so where does that work go? It is a very important question. So when I am lifting this object, the apple, from the top of the table to about half meters. So what happens to that work, right? So what happens if I release it, right? If I release it, it goes down, right? And it picks up the velocity, right? And when an object moves, we say that it has kinetic energy, Kinetic, kinetic energy, right? So when I lift the object and about this height, right, at this point, the object is at rest, so it has some kind of energy. That energy is in the state of rest, so it is in the Earth's gravitational field. So the energy here is the potential energy, right? The energy on the apple now is the potential energy, and sometimes that is also called gravitational potential energy, okay? And that gravitational potential energy, where did it come from? That gravitational potential energy came from the work I did, right? I did the work on apple. When I lifted the apple from the top of the table to here, I did work. What did I do? I did work. I lifted the apple from the top of the table to here, so I did work, right? I did work, and that work is stored as the potential energy, gravitational potential energy. So anything which has potential energy has ability to work, right? Anything which has potential energy has ability to work, right? So if I let the object go, right, so it can work, it will work, right? It will work. And now I am connecting this work done to kinetic energy. So here, when the object, I release the object falls, right? Object falls, and initially its velocity was 0, right? It was at rest, but when it falls down, it picks up velocity, and you know that velocity increase, it happens at the rate of 9.80 meter per second squared. That is acceleration due to gravity. So again, let me remind you, acceleration is the rate of change of velocity. When the object changes its velocity, right, there is net force on the object. In our case, that is the force of gravity. Basically, in this case, weight of the apple, right? When an object moves in the field of in the gravitational field, for example here, its weight does the work, right? So it picks up the velocity at the rate of 9.8 meter per second squared, right? That is acceleration due to gravity. So its velocity keeps on increasing, right? Its velocity keeps on increasing, right? Our goal here is, in the beginning it was on the top of the table. With respect to the top of the table, its potential energy was 0, right? The potential energy is given by the product of mass of the object, height of the object from some reference level, times acceleration due to gravity, mgh. That is gravitational potential energy, mgh, right? Okay, so initially in the beginning, if I consider the top of the table as the reference point, its potential energy was 0. Now I lift to about 0.5 meters, so it has now gravitational potential energy. Mass of the apple, which is 0.1 kilogram, g, 9.8 meter per second square, right? 9.8 meter per second square, h is 0.5. So if you multiply these three quantities, then you will get the potential energy. So the gravitational potential energy associated with the apple at this point is equal to mgh. Now it has mgh potential energy, right? If I let it go, now it moves and it has kinetic energy, right? Now our goal is with what velocity it reaches the original point. In the beginning, the velocity was 0, right? In the beginning, the velocity was 0, it was at rest. But when it goes down, every second every second its velocity increases by 9.8 meter per second, right? So the rate is 9.8 meter per second, which is 9.8 meter per second square, which is acceleration due to gravity. Okay, so what we would like to do is we would like to use something what is called conservation of energy. Okay, conservation of energy to calculate the final velocity. Okay, we would like to calculate the final velocity of the apple using conservation of energy. What does that mean? So here the apple has potential energy, the apple is at rest, the kinetic energy is 0. Kinetic energy depends upon the velocity squared. So since the velocity is 0, kinetic energy is 0, right? Kinetic energy is given by 1/2 half times mass of this object times square of the speed. So since square of the speed itself is 0, square of the speed is of course 0, right? So it has 0 kinetic energy, but it has potential energy. So if I let it go, at every point its total energy remains constant. Total energy is equal to the sum of potential energy and kinetic energy, right? Kinetic energy is due to motion, potential energy is due to position, right, with respect to some reference label. Always please keep in mind potential energy changes based on the reference label, where you are considering the potential energy from. For example, I am considering the potential energy on the with respect to the top of the table, right? Okay, top of the table. When the apple is on the top of the table, potential energy is 0, right? And kinetic energy is also 0 right now. But when I lift it, I do work against the gravity, right? And then I give that my work done is stored as potential energy, right? So it has now potential energy non-zero. It has some potential energy. Okay, make sense? So it has some potential energy here. Make sense? It has some potential energy. When I let it go, when I let it go, so it moves because of that potential energy and it gains kinetic energy. At any point, the total energy, potential energy plus kinetic energy is constant, right? Total energy is constant. Of course, you might think when it moves through air, there is some kind of heat dissipated, right, because of friction. But that is negligibly small, right, in this case, right? So we say that total energy is constant, okay, right? And when it reaches the floor on the original position, now the potential energy is back to 0. All kinetic energy will now, all potential energy now appears as kinetic energy. So with the help of this conservation of energy, conservation of mechanical energy, or conservation of the sum of kinetic and potential energy, right, which is constant, we can calculate at what velocity the object, the apple, reached the table. Okay, so let me show you some mathematics, right? So that will, I hope that will help you understand better, right? So let me do that. So I hope you can see my screen of my computer. What I have written is force, work done, and energy, right? So let me go to the next slide. So you see that from Newton's second law of motion, force is equal to mass times acceleration, right? So force is equal to mass times acceleration, right? M is the mass of the apple, for example. When apple is moving, A is its acceleration, F is the force. But in this particular case, we can write force is equal to weight. That is the weight of the apple. Force is nothing but weight of the apple. We replace acceleration with acceleration due to gravity, right? So weight is equal to m times g, right? Okay, then let's go to work done. So work is done is defined as force dot s. So I am introducing a new concept here, the dot product of two vectors. that dot is not ordinary decimal point, that is referring to dot product or scalar product. Okay, so f dot s, we are multiplying two vectors and the product is a scalar quantity. Okay, so you already know what is the difference between scalar and vector quantity. Force is a vector quantity, displacement is a vector quantity, you know that. So when we take the dot product or scalar product, the product gives you the work done, and that work done is a scalar quantity. Okay, and its unit is in joules. Okay, so let's go beyond. Okay, so force I have applied, there is a block here, you can see this block. Okay, so let me go to my laser pointer. Okay, so you see I have applied force here, right? I have applied force here. This is the force I applied, right? And the force is in that direction, right? And I have applied the force on this block, right? And the block moves to that direction and reaches that final point. The displacement is S. That green line right here is the displacement. That block went through a distance S in that direction, not in the direction of the force, but in the horizontal direction. So in this case, what you do is you can expand that dot product, force times magnitude of force times magnitude of displacement times cosine of theta. What is that theta? That theta is the angle between the direction of the, so I have shown here, this theta is the angle between the direction of the force and the direction of the displacement, right? So that is a new concept here, a mathematical concept, a concept in vector product, right? So the product is force times magnitude of force times magnitude of displacement times cosine of the angle between the two directions. That is the direction of the force and the direction of the displacement, right? So let's go to Apple's example, right? Originally, Apple was at point A, at point B, right? When I lifted the apple from B to A, when I lifted the apple from B to A, right? I did the work done, right? Okay, I think I missed a slide. 1 second. Work done. Okay, so that is, okay. Yeah, so the potential energy, as I mentioned, is the mgs. Okay, let me quickly go to one slide. Probably I missed a slide here. Did I? Okay, I'll come back. Okay, that is the force. Okay, yeah. So as we see, let me go back here. Okay, so what happens is, originally the apple was at point B, right? So I moved the apple to point A. So I did work on the apple. So I applied the force, which is equal to the weight of apple. And we know that the weight of apple is 0.1 times, that is m times g, right? Which is about 1 Newton or 0.98 Newton. That is the force, that amount of force I applied. So I moved all the way to the top, right? So that to point A, right? So that gives you the potential energy, which is mass of the apple times acceleration due to gravity times height, okay? And when the apple falls from point A to point B, okay, then it has certain velocity, which is v. Our goal is, we would like to calculate this velocity, right? That velocity is, of course, downward. We know the direction, but how much is the magnitude? And we know that the kinetic energy is given by this formula I just explained, right? Half times mass of the apple, in this case, times velocity squared at the point B. So that is the kinetic energy at the point B. And since the apple was at rest at point A, the kinetic energy is 0. Okay. So according to conservation of energy, right, kinetic energy at the bottom point B is equal to potential energy at point A. That means the total energy will conserve. What I am assuming here, that at point B, that is my reference level. So the potential energy at point B is 0, right? And when the apple was at point A, its potential energy was mgh, and the kinetic energy was 0 because it was at rest at point A. But the apple doesn't come to rest at point B. It falls with certain velocity to hit the table, right? So let's do one example, right? That is the apple there. Apple has weight, right? So I said that mass of the apple is 100 grams, which is 0.1 kilograms, right? So force is equal to m times g. I am considering only the magnitudes here, right? Force is equal to 0.1 kilogram times 9.80 meter per second squared, which is 0.98 newtons. So that is actually the force applied by the earth to the apple, and that is equal to weight of the apple, right? So let's do the work done, right? So how much work I did when I lifted the apple from B to A, right? That is equal to force is m times A, we calculated in the previous, m times z, we calculated in the previous slide. By the way, I have used capital W for work done and lowercase w for weight, okay? So they look the same, but they are not, right? So this is weight, but this is the capital W, so that is the work done. Work done is equal to force, which is m times g, and height I lifted through 0.5, so that is, if I calculate that, I got 0.49 joules. That much work I did, okay? So then, when I let the apple fall, right? So the kinetic energy at point B is equal to potential energy at point A. The potential energy at point A is nothing. That is just I calculated in the previous slide. That is equal to work done. Okay, work done. Whatever work I did, that all is stored in as potential energy, right? So that potential energy now converts to kinetic energy. So the kinetic energy at point B is equal to potential energy at point A, okay? So then if I simplify, kinetic energy is equal to half mv squared. So potential energy equal to the quantity which I calculated in the previous slide. So that if I do that calculation, then I get that the velocity of the apple when it hits the table back is 3.1 meter per second, right? So it is in downward direction. That is the magnitude of the velocity, right? So that's how we can estimate the velocity of any object, right? If we know with what is its initial potential energy, right? If we know what is its potential energy and how much is its mass, then we can estimate, we can predict, we can calculate the final velocity or the velocity at some time later, right? That is because of conservation of energy in Earth's gravitational field. Okay, so with that, I would like to thank you so much for watching me. So if you have any question, please leave your comment or feedback in the comment section, or you can also leave your comments in my inbox. Thank you so much. See you next time. Bye.